I work at Internet Security Systems, and today I'll be talking about one of my fun side projects, the stuff I do on Friday nights, in my spare time. I'll be talking about ELF runtime binary encryption, specifically about Shiva, which is a tool that Sean Close, a good friend of mine, and myself have written. Sean works for Secure Reality in Australia, and he wasn't actually able to make it here for Black Hat this year, but everything I'm talking about has been done by both of us. The first thing that some of you might be wondering, most of you probably know, what exactly is runtime binary encryption? And it's very simply encrypting an executable such that it's encrypted on disk, and anyone who goes to look at it is going to see that it's encrypted on disk, but it executes as it normally would within memory. So it's resistant to analysis and modification. And hopefully it's resistant to analysis and modification while executing as well as on disk. So it's resistant to static analysis as well as runtime analysis. About ELF, or ELF, it stands for Executable and Linking Format. It's the standard executable format on most Unix platforms. And I won't go into great details about ELF because I don't want to bore everyone here. But it consists of the standard components of most executable formats, such as a header, which contains generic information about the executable itself. And then there are section and segment headers, which contain specific information about different parts of the executable. Other portions of an ELF executable might include symbols, string tables, and relocations, which all function in different ways to make the executable execute. I'll also give a very, very brief and quite incomplete history of runtime binary encryption, just to give you an idea of the context in which Shiva fits. Up until quite recently, in the last year or two, runtime binary encryption has been pretty much confined to Microsoft platforms. So DOS, Windows, and anything other than that has been pretty much ignored by people who've been writing runtime binary encryption tools. Going back really far to before I even used computers, the first runtime binary encryptors actually encrypted .com files. And honestly, there really is no format to a .com file. It's just executable code. There's no header. There's nothing. It loads at a static address, and it has a limited amount of space, and it just runs. And so it would be very easy to write a binary encryptor that encrypts .com files, because all you have to do is actually encrypt the data and decrypt it. But they also start at they always begin execution at a static address of 0 by 100. So quite often you'd see generic decryptors for these common encryptors, because after the runtime encryptor is finished decrypting the file, it goes back to execute this same address every single time, 0 by 100. So you just sit there and wait till it executes that address, at which point the file is actually decrypted in memory, and you can dump it and run it as normal. So these weren't very successful. There are obviously one or two ways around that, but common encryptors weren't really important, and they weren't really a significant part of runtime binary encryption. Onto Windows. With the portable executable file format, PE, there's a lot more stuff that you can do to make an executable hard to decrypt, hard to analyze, and hard to modify. I would say that the pioneer in Windows PE encryption would be PEcrypt, which came out around 1998 and was written by 3 guys who were part of the reverse engineering scene. And it was kind of an eye-opener for people. They hadn't really seen anything that modified an executable to the depth that it did. And it was kind of a guide or a pioneer for future PE encryptors. And today you'll see that, I'm sure quite a few are familiar with ASPAC or UPX. And they really dominate the encryption or runtime binary encryption field on Windows. And as part of my job, I do a lot of malware analysis, viruses, worms, and pretty much every Windows worm or virus that I look at is encrypted with ASPAC or UPX or something similar. And so it's very, very significant to anyone looking at any type of malware out there. Honestly, it doesn't really do much to make it hard to analyze. I'm sure people unwrap them in seconds or minutes, but people use them anyways, and they're definitely out there. On Unix, the first Unix runtime binary encryption tool that was of any significance was Bernai. That was released in 2001 by Scott. I believe his real name is Sebastian, and it was I guess the PE crypt of Unix runtime binary encryption. It was a pioneer, and it offered some reverse engineers a chance to actually look at runtime encryption on Linux and on ELF files. And I believe now that UPX also supports Linux, but up until 2001, there really wasn't anything, and since then, there have been a few small encryptors here and there, but nothing extremely significant that is nothing that anyone's put a lot of work into to create. So those are the two right now. Up until this year, where Sean Close and myself released Shiva, and Shiva is a runtime binary encryptor for Linux x86 executables. We haven't really expanded beyond that, although we do have plans in the future to do that. And it's designed to bring a lot of the techniques that have been used in Windows, as well as new techniques, to the Linux platform. A little bit about the difficulties involved with runtime binary encryption. The encryptor's dilemma is what I call it. To be able to actually execute the executable, the code has to be there. It must be able eventually be decrypted if it's going to be run. And so no matter how hard you try, or no matter all the steps you go through, you still have to end up executing that code. So it must physically be there in memory for you to be able to execute it. And so that being said, binary encryption itself turns into an arms race. It's really who has more time to put into creating the encryptor or breaking it. And I'll be honest with you, there are probably a lot more people out there with more time than me to do it. But it's essentially someone will create an encryptor and then someone will break it, and then you're going to fix your encryptor and then they'll break it again. And it goes on and on and on. And it can be quite tedious at times. But honestly, in the end, the encryptors cannot win. And simply because you don't know if someone has broken your encryptor out there. You have no idea what attacks are being used unless people tell you about them or make them public. So because of the fact that the executable has to execute, the code has to be there, and unless someone is nice enough to tell you, you don't know what attacks are being used to attack your encryptor, you really cannot win in the end. You can make life really hard for a determined attacker, but it's really a losing game, but it's not a pointless game. And quite often, people who are novice reverse engineers or people without very much experience or people who really don't care about reversing your encryptor or your executable that's encrypted with it won't put the effort into doing it. So there's that part to it. I think I quickly touched on this before. If the encrypted executable has access to the encryption keys, then an attacker could potentially have access to those encryption keys too. So a solid attack would have to be able to retrieve those keys and then use them to decrypt the program. So once again, you can only really slow a determined attacker, but there's a lot that you can do to make their life really, really hard. Our aim, Sean and myself, our aim was to introduce some new techniques and advance the state of the art. As I mentioned before, Unix executable encryption was a neglected field. The technology out there was pretty easy to get around, and anyone who knew what they were doing could decrypt any executable encrypted with the previously released encryptors. So we wanted to make it a little bit hard, and also, kind of as being part of a reverse engineering community, we wanted to promote interest in reverse engineering on Unix platforms. So those are some of our goals. What's really the point of runtime binary encryption? It's good for several things. You can prevent the trivial reverse engineering of algorithms in your programs, or the content of the program. So if you have some really, really great piece of software and you're releasing it to the public, but you don't want the internal details of that software to show up in other programs or people to steal them, you can use a runtime binary encryptor to go ahead and obfuscate the code within your program. From an administration standpoint, you can protect set UID programs with passwords. So it's just an extra layer of security there. And yeah, hide sensitive data or code in your programs. There are some very common attacks that are used against binary encryptors on Unix. And there's a big list of them right there. But strace or ltrace is what they do is they monitor system calls or library calls. And they're quite useful to get a quick idea of what a binary is doing when you're executing it. They're very useful. I use them quite often. And a good encryptor will have to be able to deter these standard attacks. Fenris is a execution path tracing tool. It was written by Michael Zalewski. And strace, ltrace, and Fenris are all based on the ptrace API. GDB is the standard Unix debugger. And once again, it uses a ptrace on Linux. The procfs file system on Linux actually can allow you to dump memory of executables that are running. So if you're going to deter attacks based on the procfs, the encryptor should be able to do something about that. And then everyone's favorite tool, strings, which is the tool of every good reverse engineer. I'm just being facetious, but any encryption of any sort should deal with strings. So if you encrypt the binary in any manner whatsoever, the strings won't be there. People won't be able to guess based upon the data within your executable. ltrace, strace, Fenris, GDB, they're all based around ptrace. So making that API ineffective would be a big step towards making a binary encryptor difficult to attack. And I'll go into how we do this later. The procfs file system is attacks based on that would be memory dumping attacks. And those attacks would be based on the assumption that all or a good portion of the executable is decrypted in memory when you go to the /proc and try to dump the memory. And that's not necessarily true. And a good encryptor will do something to invalidate that. So I'll go into how that works later. All that aside, there are still static analysis attacks. And if you leave static analysis as one thing that we're not going to think about right now, all these active attacks can be detected by an encryptor. And the encryptor can do something to prevent them, and maybe something even a little bit worse, such as I don't know, killing the debugger, or you can go beyond that. Shiva doesn't do anything like that, but there's a lot of stuff you can do to detect these active attacks. But static analysis is always a concern, and if someone truly understands your encryptor, they can go ahead and exactly replicate the decryption process, and there's nothing you can do about it. If they understand it to that depth, then the game is up, and there's absolutely nothing you can do about it, because you can't detect it if they've completely reverse engineered every part of your encryptor. But to make that harder, you can take a layered approach to runtime binary encryption by adding not just one layer or two layers, but many layers. There's a really bad metaphor in there, like an onion skin, where you just peel away one skin and there's another one under it, and so on. So making it more difficult by taking a layered approach is something that Shiva does. Another thing that most encryptors don't take into account is how predictable their behavior is. Most encryptors encrypt an executable the same way every single time. So if you run the same encryptor against the same executable 5 times, you get the same output. And it will behave the same way, do the same things. And so if you understand the way it works on one executable, you can understand the way it works on every single executable every single time. And this is why you see a lot of generic unpackers out there for UPX or ASPAC, because their behavior is very predictable, and if you understand how it works once, you understand how it works every time. So any step that you could take to make the encryptor behave differently from one executable to the next, or one encryption instance to the next would make it harder for an attacker. So the less generic the methodology it is, the harder it is to create a generic unwrapper. So yeah, I'm not just talking about this thing for no reason. Shiva tries to do all of these. It tries to implement all of the defenses I've talked about. We didn't quite make it up to Shiva version 0.99. I guess we're at 0.96, which is on your conference CDs. 0.97 should be out very shortly, which includes some pretty interesting changes. It's not quite at a full release version of 1.0, at least not what I would think would be. So we'll see that sometime in the near future. What it does is it encrypts dynamic or static Linux ELF executables, but it doesn't handle shared libraries yet. So that's a future product for us to look at. A little bit about developing an encryptor. An encryptor itself is really two completely separate programs. You have the program that does the encryption and outputs the executable file, and then you have the decryptor, which is embedded in the output file and behaves in a symmetrical way to the encryptor so that it actually allows the program to run. The encryptor for Shiva is a normal executable. It's just a regular ELF executable. It does the encryption process, it wraps the executable, and gives you a nice output file. And the decryptor itself is a statically linked executable. So it contains all of the libraries that it needs to use. Actually, it doesn't use libraries, but and it performs the decryption and all the runtime processing. So it's a little bit more complex than the encryptor itself. And it has to be embedded with within the encrypted executable. It has to be self-contained. For size concerns, we don't link it with libc because you don't want to encrypt a 20K executable and end up with something that's 5 megabytes or something. So it doesn't use libc, which is a little bit of a pain to start, but it's a lot more efficient. One thing that we ran into when starting to develop Shiva was dealing with the ELF format and what's the best way to do it. And it's a reasonably complex file format. There are a lot of different fields within the headers, and I honestly got very tired of using static offsets into headers to go ahead and look at the data in the headers. So we developed an abstraction API which will read any ELF executable into a well-defined structure in memory, allow us to manipulate that structure, and at that point, at any point, I guess, write that structure back to a working executable. So it made our lives a lot easier when developing Shiva to have this in place. At any time, you can go ahead and modify the size of the image within the header, or you can modify, go ahead and change some of the different segments and expand them. And it was a little bit of overhead to actually develop this, but I mean, it's not that revolutionary. But it did make developing the encryptor a lot easier, and it took away a lot of the headaches involved with doing it. Shiva itself has a what we call a dual process module, where it when any Shiva encrypted executable runs, there are actually two main processes that run, and they interact, and they're dependent on each other, and I call it the evil clone. But there's a slave process, which is actually the main executable thread, and it runs the code that was intended to be run by the executable. And then there's a controller process, which is the clone, and what they do is they ptrace each other. So if you're familiar with the ptrace API on Unix, you'll know that there's a hard limit of one ptrace instance per process. So any process can only be ptraced once. So this ptrace is functional, and it also serves an anti-debugging feature, because if they ptrace each other and that link is established successfully, then supposedly without kernel modification, no other executable can actually try and ptrace either of them. And of course, you can go and modify the kernel and get around that, but it's a fairly significant part of Shiva. Another part of Shiva that we implemented was runtime generation of x86 assembly bytecode. And we do that from within C. So we implemented a very basic assembler that creates this code on demand. And it allows us to do pseudo-random code generation, or basically make the encryptor behave differently each time it's run. a little bit differently anyways. It's pretty challenging to make it behave completely differently from time to time, but there is some pseudo-random code generation, and each time you run it against an executable, you get a different output, and you'll get code that behaves slightly differently. And as time goes on, we'll make it more different for each instance and a lot more challenging to look at. But this functionality makes it harder to write a generic unwrapper. And it also was a fairly, well, I wouldn't say it was hard to develop, but it was a fair amount of work to do. But I think it's worthwhile doing in the end. OK, I just lost everything there. All right. So as for the layered approach, Shiva starts out with a very, very basic obfuscation layer, which is generated by the on-demand bytecode generation. And all it does is it does a very simple encryption of all the data in the executable and all the data in the decryptor itself. So if you think about it in layers, you have your obfuscation layer and you have all the obfuscated data below it. And the only real purpose of this is to make it difficult to reverse engineer the decryptor itself. It serves its purpose. It's very easy. It's very quick. And if you wanted to get around it, you could. But it's definitely not the only defense. It's intended to evade simple static analysis. And yeah, as I said, it's somewhat random, and it's generated by the inline ASM generation code. Beyond the obfuscation layer, there's a password layer. And if you choose to use a password, you don't have to. But if you choose to use a password, the password layer is there, and everything other than the password layer and the obfuscation layer are encrypted with AES. So if you choose to add a password to an executable, and provided your password is strong, there is a very significant obstacle to any reverse engineer. If they can break 128-bit AES, they can go ahead and decrypt the rest of the executable. If they can break your password, which is more likely, then they can decrypt the executable. But if they can't do either of those, then they're stopped dead in their tracks, and there's nothing more they can do. The key for the decryption is just a SHA-1 password hash. So it's only as strong as your password, but I think everyone knows how to create a reasonably strong password. And the password layer itself is a very significant obstacle to anyone if you add it. The third layer is the crypt block layer. And the way this works is the executable is divided up into hundreds and hundreds of different blocks of data or blocks of code. And these are encrypted and decrypted at different points within execution. There are two different important types of crypt blocks, ones that are immediately mapped and ones that are mapped on demand. So for simplicity's sake, we map all data immediately because you don't know when the data might be accessed. You don't know what part of the code might access the data. So you have to map the data immediately to make sure it's there and the program can execute properly. But as for code, for most, if not all executables, code is not important unless it's actually being executed. So it doesn't have to be there unless you're actually running it. So Shiva can leave a certain percentage of the code encrypted and only a small percentage decrypted at any given time. And the controller process, the clone, handles mapping and unmapping the different crypt blocks at any given time. So if you're actually running the executable and you're within a decrypted block, you start out within a decrypted block. And say execution flow brings you to a block that is actually encrypted. It'll generate a fault which is caught by the controller process, and the controller process goes ahead and then decrypts that. And when it does that, it also randomly unmaps some other blocks out there, so that as the executable runs, you don't have the problem of having more and more of the data or the code unencrypted as time goes on. So there's a random unmap feature. Also, to create these crypt blocks, you have to be able to parse x86 instruction lengths. It's not trivial to do that, but it can be done with a little bit of work. And I really wish x86 was a fixed length instruction set, but it's not. So you have instructions that are 1 byte, 2 bytes long, 8 bytes long, and you have to be able to understand that to have make sure that your crypt blocks don't end up on or in the middle of any instruction boundaries. So that's part of Shiva too. So as you move from a cleared block to a decrypted block, the block becomes decrypted, another one becomes unmapped, and the block content itself is encrypted with a strong algorithm. So it's a reasonably simple and reasonably efficient algorithm, but it's strong. I'm not going to tell you what it is, but if you take the time to reverse engineer Shiva, you can go ahead and probably guess what it is pretty quickly. The keys aren't stored as data within the executable, because that would just make it too easy. So they're never stored in plain text. There's code that generates the keys on the fly. And it's made pseudo-randomly by the ASM bytecode generator again. And to take it to the next step, this code itself tries to bind it to a specific location in memory. So you couldn't just rip the code out and run it within the context of another process. You'd have to do significant modification on the code to make it work. So it tries to make it very hard to take this code out of the context of the Shiva process. And it makes it a little bit harder to find the keys. The dynamically linked ELF executables, pretty much every executable on your Linux system is dynamically linked. And they interact with the system's dynamic linker to resolve references to libraries and resolve references to any external symbols. And it's quite a complex process, and when we developed Shiva, we chose not to try and replicate that, because that itself would be an incredible amount of work to do. So the decryptor itself has to map in the system's dynamic linker. And it passes off control to the dynamic linker. The dynamic linker goes ahead and does all the horrible mess that is resolving all those symbols. And Shiva has to regain control again after the linker is done. And that's done by setting a certain member of a structure which you pass to the dynamic linker to one of the Shiva routines, which does that. Another part of Shiva is anti-debugging or disassembly. And it's a pretty important part of Shiva. If it was easy to debug it, it would be easy to figure out what it did. And I know I'm telling you what it does here, but still, we didn't want to make it too easy to debug or too easy to disassemble. So there's, as I mentioned before, there's an inherent protection offered by the dual ptrace approach. And it's not just a link there for this, like a ptrace link there just for the sake of being there. It actually serves a purpose. So if you get in between that or you break that link somehow, you ptrace one of the processes or the other, a Shiva encrypted executable will just stop working. So that itself makes it a little bit more difficult to break Shiva. But of course, you can do modifications to your kernel and try and get around that. So there are a lot of other anti-debugging things that we put in there. Shiva checks the flags register, which can be accessed via procfs. And if someone has tried a single step through a program, the trap flag will be set in the flags register. And that tells the CPU to generate an interrupt at when every single instruction is executed. So it allows a single stepper to gain control of the process and go ahead and analyze what it's doing on an instruction by instruction basis. So by looking for that, we can try and invalidate that attack. Also, by checking proc self stat, you can tell if your executable is being ptraced by another process. So that's just a small step that can be taken to determine if someone is trying to reverse engineer a Shiva encrypted executable. There's some other stuff in here. There's something to do with timing and sigtrap. And I didn't write this code, so I honestly can't remember how it worked. I tried to look at the source code today and figure out what Sean was doing there. But his comment said, I'm going to quote him here, it said, "I'm not sure why this works, but it does." So I can't remember specifically why that works or what it does, but it's, there's also a simple sigtrap cache within Shiva, which plays havoc with a lot of debuggers and allows you to detect them. As for anti-disassembly, this is a really old trick, and it's been around for years, and it's been used by a lot of people, but on x86 or a lot of CPUs that don't require a fixed instruction length and don't require any alignment for those instructions, you can do a trick which I call jumping into instructions, which is if you have an instruction that should be 8 bytes long, the first 2 bytes could be whatever valid data it is, and the last 6 could be code that continues on. So if you were to jump 2 bytes into that instruction and have the real code there, a disassembler looking at that will think that's an 8-byte instruction, and it will parse it as an 8-byte instruction, and the code won't make very much sense when you're looking at it from a disassembler. So I'll show you that a little bit later within IDA, how that looks and how it plays havoc with anyone trying to read the assembly code. Another thing that we do within Shiva is bytecode manipulation. And this is another layer beyond ELF. This is going beyond the ELF file format, and it's going actually to the x86 bytecode. It's currently x86 specific, as is the rest of Shiva. But what we're doing is we're looking and parsing the executable code and looking for specific code constructs that we understand. And we process each instruction, and when we find stuff that we understand, we go ahead and we can make modifications to those specific instructions. Doing this requires a lot of code analysis, and it was a reasonably large amount of code to put into Shiva, because you have to recognize code flow within the executable so that you don't get it wrong, you don't change something that you think is a push, or for example, I don't know, an XOR instruction, when it's actually a MOV instruction, then you just got the instruction boundaries wrong. So to get it right and to do it reliably requires a lot of processing and a lot of code, and a very well-designed framework to do it. And we've implemented something within Shiva that works reasonably well to do this. There's some easy things that you can do when you're manipulating bytecode. An obvious one would be to redirect calls. So let's say someone is a pretty good reverse engineer, and they've gone and broken they've removed the obfuscation layer on a Shiva executable. And they've gone beyond that, and they've cracked your password on the Shiva executable. And they've gone even beyond that, and they've found out and figured out a way to decrypt all the crypt blocks. So they have all the data encrypted or decrypted, and they have access to all of it, and they go ahead and try to run it, and it crashes at some random place. And the reason why it crashes is because you've changed the call instruction, and it points to the wrong place within the executable. And so it's just an extra layer that makes it harder to completely decrypt an executable. You could redirect calls to anywhere in memory as long as it's the wrong place. A little bit trickier thing to do would be to redirect to somewhere that looks legitimate but actually isn't, so it would be harder to recognize. Jumps are the same thing. You can redirect them anywhere, and Shiva plays with those a little bit. Jump tables are constructs that are created by the compiler that they're usually created to handle switch statements. And so if you have a switch statement with 20 different cases within it, the compiler will create a jump table that points to each of those cases. So by modifying these jump tables, you can make it a little bit harder to decrypt the executable fully also. These are usually stored in the read-only data section of ELF executables. I know on Windows platforms they're stored within the code, which makes it harder to analyze them a little bit. And there are a lot of other constructs that you can deal with also, like handling simple instructions like common instructions associated with function calls, like push instructions, push EAX, for example. If you change it to something, change it to something that change it to an int3, let's say, that Shiva can intercept, an attacker will have no idea what was previously there unless they understand what Shiva has done to it. So this is just one extra nasty layer on top of everything else to make an attacker's life harder. And the way Shiva deals with it right now is it emulates the instructions that it replaces or takes out. And this is done by, Shiva has access to the ptrace register structures because when it replaces an instruction, it puts an int3 in that place. And the controller process actually, when it takes control of execution, has access to a structure which contains information on every single register. So it can modify the stack pointer, it can modify the frame pointer, it can change any of the general purpose registers. And because it executes in the same address space as the main thread, it can go ahead and access memory and change memory very easily too. So virtually any instruction that you can think of can be emulated by this approach if the decryptor or the encryptor understands what that instruction is doing. So if you had, I don't know, an instruction that does mov EAX from EDX times 4 plus some static address, if the bytecode analysis engine of Shiva understands that instruction and replaces it, it can emulate it by looking at the register structure, finding EDX, multiplying it by 4, adding the static address to it, and then dereferencing that address to get the value to put in EAX. So there are routines within Shiva which do this, and I think it's a fairly effective way to make it harder to go ahead and decrypt a Shiva executable. We encountered quite a few problems when trying to create Shiva. Establishing the ptrace link is quite a hard thing to do, or at least it's not very intuitive as to what it is you need to do, because when one process ptraces another, there's an exchange of signals between the two. And if two processes are trying to ptrace each other, the signals being sent back and forth cause the process to go into an endless signal delivery loop, because the ptrace API communicates the signals that are sent to the tracing process. So to establish this link, you have to block pretty much every signal and then enable them after the link is established. Another challenge that we encountered was, how do you handle fork? Because for a Shiva executable to run, you have to have the ptrace link there, and you have to have both threads running. And if they're not there, it's going to crash very, very quickly. So when a fork is encountered, it has to be intercepted by Shiva, and the cloning process has to be reestablished. So what Shiva does is it patches into the fork routine within libc, and it intercepts any execution of the fork system call. And what it does is it runs the system call, and then after that it establishes the ptrace link and the clone process again. And once that's done, the forked, the child can continue to execute without any problems. Exec is a little bit different, but it also has to be handled. If a program tries to execute another, there's no need for Shiva to be there in memory at all anymore. So when we encounter exec, all we do is we undo the ptrace link, get out of the way of it, and allow the exec to occur, so that there's no longer anything to do with Shiva within the child process. I mentioned this a little bit before also. libc makes programming a lot easier, and if you're trying to do a lot of stuff without libc, you have to rewrite a lot of those routines. For example, trying to write a complex program without a malloc is a major pain. And what we ended up doing was implementing a small and very simple implementation of malloc, which allows us to allocate dynamically sized buffers. And you can imagine trying to write a decryptor without having this available to you. It's very, very hard and almost impossible. And of course, we replicate a lot of the simple routines within libc that you use on a day-to-day basis too. So that was another challenge that we encountered. There are some limitations to Shiva. First thing is, it can't handle vfork, and it definitely doesn't handle threads very well. Vfork is just something we haven't taken the time to add, and I'm sure we could add it very easily. And multi-threaded programs on Unix are quite rare, so I haven't really seen a need to implement any support for threaded programs yet. but that may change, and we may have to do that in the future. I believe that Apache can run multi-threaded, although it definitely doesn't by default. I'm not sure what else can, and there's some very serious problems with pthreads on Linux, so I don't really want to go there, but we may have to in the future. On Linux, exec fails if a Shiva encrypted program tries to execute a setuid program, and this is because of the ptrace link. This, once again, can be bypassed, but we haven't taken the time to do it yet. Another limitation of Shiva right now is section headers. It relies on section headers, and section headers are nice information to have in an ELF executable, but they're not necessary. All the necessary information is in the program headers, which tell you which segments to map and load. So you don't need the section headers, but Shiva relies on them just because it's an easy way of getting information about the executable. So in the future, we'd like to remove that dependency on section headers and make it work on virtually every possible ELF executable out there. And this isn't really a big limitation because any executable that you compile is going to have section headers. And unless you take the time to take them out, every executable on your Linux distributions will have section headers too. So it's not a major problem, but it's something that we'd like to eventually remove. We had planned to remove them by the next release. That was a few months ago, and we still haven't done it. But we might get around to doing these things. I'll go into a demo right now, show you how Shiva works, and a little bit about how a little bit about Shiva in action here. Okay. So what I have here is I have the binary release of Shiva, the one that you have on your conference CD. Actually, the one you have on your conference CD is a copy of Shiva that's encrypted with itself. So the first thing I'll do is just show you, it's kind of neat that it can encrypt itself here. Just specify the executable to encrypt and let it go do its thing. And we have a copy of Shiva that's encrypted with itself there. And let's see if it still runs. And yes, it still does. So I thought it was kind of cool that an executable can encrypt itself. When it comes to runtime binary encryption, a lot of executables can be used to, or a lot of different runtime binary encryptors can be used on the same executable. So you can chain one on top of another and have, I don't know, 5 different binary encryptors used on the same executable. And a lot of them work that way. Shiva is less likely to work that way because of all the anti-debugging stuff that it does and the dual ptrace link and everything. If you're looking to apply more than one binary encryptor on any given executable, you're probably best off trying to apply Shiva last. It's most likely to work there than anywhere else. But we can use Shiva now to encrypt. Does anyone have a request for a program? Lilo? Bash? I'll try something small first, bin ls. So it's created an encrypted version of ls here. I don't know why you'd want to do that, but you can if you want. That's the original version, so it's about 22, 23K bigger. So it's not significantly bigger. And it works as the original executable did. If you want to try and look at, try some strings on it here, it's all garbage. There's nothing useful there. So I know there are a lot of reverse engineers out there, or people think that they're reverse engineers because they use strings on binaries that they get from the wild, and they see that it tries to open Etsy password, and they think they know what it does. And as you can see, there's no useful information that you can obtain from strings here. If you want to try and debug it with GDB, which you see as a sig trap, and it just exits. So the anti-debugging picks up GDB very well and makes it quite difficult to use GDB against this. We can try strace, and as you can see, it dies right away too. ltrace would be exactly the same. We can try adding a password to an executable maybe. You can encrypt your shell. Hold on 1 second here. This laptop is horribly slow. I had to grab one out the door yesterday, literally. So bear with me here. But the, I don't know, let's use my favorite password, ABC123. You can check my email with that if you want. And if you don't have the password, I'll just type in something random here. It just exits. If you have that actual password, it's actually run a shell here. You can't really tell, but if I exit, you'll see my my terminal doesn't die. So that was kind of a bad thing to demo. But without a password, there's very little you can do to get around Shiva. I guess I can also show you what an encrypted version of Shiva looks like when you try to disassemble it. If I can get out of this here. I use IDA, which is pretty much a standard on for our binary analysis. First thing it tells you is the file contains meaningless or illegal section declarations. Oh, you can't even see this. I'm sorry. Switch it back here. So that's the first thing it tells you right there. Older versions of IDA used to just tell you that, and it would just exit, which I thought was pretty cool, but they fixed it since then. And it goes ahead and it tries to disassemble the binary. This is what you end up with. You end up with 3 instructions, a couple more down here. That looks like code. And a whole bunch of junk data. This goes on forever. Well, let me show you the jump into the instruction trick here. If you look at, I don't know if you can read this, but at this point here, the instruction that I've highlighted in yellow there, it's jumping to that address plus 1. And the following instruction is a 5-byte instruction, mov EAX some value. So IDA interprets that instruction as being 5 bytes long, when in actuality you're jumping past the first byte, which is insignificant, into real code after that. So if you want to take the time to manually go and fix that, you can try and do that. The next instruction is pop EAX. But to do this for an entire program is very, very tedious and not very feasible to do. So as you can see, there's very little information you can gain from doing simple static analysis on a Shiva executable also. I don't know what else I can show you about this here. I think this is code here that, that passes off control to the dynamic linker. So that's the one part that is decrypted. But other than that, there's very little information that you can actually gain from looking at the file itself. I'd like to take any questions if anyone has them right now. The question is, does Shiva modify libc? It does modify the fork routine, but it does it within memory. So it places a jump instruction that points to a Shiva routine within libc fork. So the modifications obviously aren't permanent, but they have to be there for us to gain control at any fork. Yes, sir?
Have you done any analysis on the impact of execution time of encrypted programs?
Yes, well, not any formal analysis, but just very qualitatively, they do run slower because it would be obvious, I guess, but as you transition from one decrypted block to an encrypted block and so forth, there's a little bit of processing that has to be done, plus there's an interrupt every time you do that. So that slows it down. You're not going to want to encrypt your web server with Shiva and run it because there would probably be a significant performance hit at that level. But for simple programs or programs that you're going to run at the console, it's not noticeable. Actually, the more recent version of Shiva has a little bit of more of a performance hit than previous versions because you get an interrupt when you encounter a crypt block. You also get an interrupt when you encounter an emulated instruction. So there's a little bit more of an overhead in the newer version of Shiva. And I do plan to add some sort of more intelligent way of picking the instructions that we emulate so that you don't end up with an instruction emulated within a loop that's executed over and over again, generating an interrupt, because that can cause a significant slowdown. And I think that we have the framework in place with the type of code analysis that we're doing right now to detect those loops and detect those situations and not actually replace those instructions. But you can run into the rare case where Shiva has bad luck and happens to pick one of those when encrypting your executable. And you can just run Shiva against it again, and it'll pick something different, and you won't have that problem. Yes?
When you have a password-protected binary, what is the process that it goes through when you enter the incorrect password to determine that it should be saved?
Okay, the question is, what is the process that Shiva goes through when you enter an incorrect password? We used to just let it crash and not go through any process, and that's probably the safest thing to do. But what it tries to do is it decrypts a certain section of memory and tries to verify a tag that's there. So it encrypts a large block of itself, and if a tag isn't at a certain location, a specific string that should be there, then it knows that it's been decrypted wrong and it exits. And I guess that opens it up to certain attacks, but I don't think it's really that significant. And you're not going to be using Shiva for anything that sensitive, I think, so it's not really a big concern. Yes? They're not actually stored as data within the executable. There are routines that generate them and return. So these routines are called by Shiva, and they return a key which Shiva uses to decrypt the crypt block. So the thing we were trying to avoid was just leaving the keys out there in memory for anyone to grab and go ahead and decrypt the entire executable. That would just be the worst thing. So we tried to make it a little bit harder by making these routines generate them at runtime. And the routines themselves, as I mentioned before, try to bind themselves to a certain address. So they might try to bind to address 0x8081234 or something, right, within the executable. And they might look for data at, I don't know, 1,000 bytes beyond their location and use that, and look like 1,000 bytes back and use that. And the reason for that is to make it hard to take these routines out of the context of Shiva and just generate the keys in another executable. So we've tried to make it harder to get at the keys, but I suppose it is possible to do. Yes? The question for those who didn't hear it was, there's an inherent structure to ELF executables, and there's plain text that you know will be at a certain location in memory, and it will always be there, and that could be a weakness. Honestly, plain text attacks were one of our biggest worries, and we haven't really done very much to try and discourage that, simply because the key space is pretty large. It's 128-bit, and it's not going to be used, or at least we don't think it's going to be used for anything that sensitive. But I have used that specific thing to break some very weak ELF encryptors out there. Like, you know, the entry point of a Linux x86 alpha executable might have these 4 instructions to start. And if you know what the entry point is, you can break some very weak ELF encryptors out there. The encryption within Shiva is not that weak, and it's not like a simple XOR or something stupid that you could use to immediately break based on plain text. Yes?
Is Shiva, is it available, and if so, is it exportable to ISS's relationship with this government?
Shiva actually has nothing to do with ISS, other than the fact that I work at ISS. You can get Shiva off the, Sean was nice enough to host it on the Secure Reality website, and you can download it from there. So I'm not sure what the export restrictions are on it, but it's downloadable from Australia, so hopefully that doesn't affect us. It's also on your conference CD, so if you want to get it from there, that's fine. And we should be putting up a new version on the Secure Reality website within the next couple days that implements a couple new ideas. So if you're interested, look out for that. Yes? Sean and I had originally promised to release the source code 3 months after the initial release of Shiva, and we didn't do it because I don't know that releasing the source code really, I mean, it's a good educational experience for people who want to read it, but it kind of invalidates all the work that we've put into Shiva. And I'm doing a good enough job of doing that right now by talking about it and outlining everything that it does. The source code would make it even a lot easier. Also, I mean, we may choose to release the source code in the future. We haven't set like a clear date for that or anything. I do want to clean up parts of it before we do any release, because you know everyone writes messy code sometimes. But we may in the future. I don't know if we will yet. Yes? Yeah, we don't actually deal with anything at the kernel level because there's no guarantee that you're running as root, and there's no guarantee you can actually verify any of that. Using LD preload to load a library would be a good way to start attacking Shiva, because we don't verify that yet either. But I think that maybe the next release, I'm not sure if Sean has added it yet or not, but if you want to attack it right now, do that, and it's a very good way to do it, sure. Yes?
Have you done any work with Shiva in terms of enforcing pre- and post-conditions on a specific function? It seems that it's already used for that, as a useful tool, I think, in the right role.
What do you mean by pre- and post conditions on a specific function?
Restricting argument values.
Oh, I see. I hadn't thought about that, but the code analysis engine within Shiva can understand with a lot of detail the structure of an executable and how it executes, where this routine is called from, and so on. So you could potentially insert code into an executable that does that. I hadn't really thought about that, but that's a pretty interesting idea. Any other questions? Yes? The question is, do we use any anti-reverse engineering or anti-debugging methods on the controller code, right? We try to use anti-debugging as early in the decryption process as possible. We don't want to decrypt half the executable and then start running the anti-debugging and figure out something's wrong. So I think that there's anti-debugging in the very initial obfuscation layer, which is the very first thing, and then there's more of it placed throughout the decryptor itself. So there's no one specific place where you might look to go ahead and disable the anti-debugging. We try to make it a little bit harder by placing it throughout the execution process, but we try to verify as early as possible that it's not being p-traced and someone hasn't attached a debugger to it. The controller code itself isn't modified in any great detail. So it's basically a static executable that we put in there. The only steps we take to obfuscate it are the first initial obfuscation layer. But the version that's going to be released very soon, version 0.97, in fact, it might actually be released now. I'm not sure. I haven't had a chance to actually get on the internet and check it. But the version that will be released adds some more steps to the decryptor itself, such as removing static function calls. So if you wanted to reverse engineer and you wanted to see where a function call goes, it goes through this complex and obfuscated table that makes it very difficult to figure out exactly where the call is going. So for example, a call going through this function table itself will modify that table. So it changes on a call-by-call basis. And that requires some understanding of how the decryptor works and the state of the decryptor at any point. But that should go a certain way to make the decryptor hard to reverse engineer. Any other questions I can answer? Okay. Thank you for your time.